Good day, this is Bennett, also known as Jeremiah. Today we're going to talk about the whole photoelectric effect, including past papers, all in 39 minutes. If you're interested in more videos, the playlist is found at the end of this video. It is also found right here on the top right of the screen at the suggested video. So, let's begin. Alright, let's first talk about what we call the dual nature of light. So there is what you call the dual nature of light, very important. So, number one, there is what you call the wave nature of light. In other words, light is a wave, right? So light is a wave. So in the lower grades, we learned how that light was a wave. But we're not going to go deeper into that because it's not going to be important in this grade. So there is also what you call the particle nature of light. So light behaves in two ways. There's what you call the wave nature of light. There is what you call the particle nature of light. So in the exam, whenever they give you a diagram, let's just say we've got a certain circuit. And let's just say we've got something like this. So let's just say we've got a certain circuit. So if they give you a circuit in this topic, and they ask you, let's just say light is shown, right, on this metal. And they ask you what nature of light is demonstrated here, you have to say is the particle nature. So I'm going to explain it in a moment. But one thing you must know that in general, photoelectric effect is just about the particle nature of light. So let me talk about this in detail. So number one, light is made out of photons, right? So it's like packages of energy. So light is made out of photons. So everything we see on Earth, everything, even when it comes to air, everything is made of mass, right? So everything that we see, every object, even the wind and stuff, everything is made of mass. However, light is not made of mass. Light is made out of photons. So it's made out of photons. So this is why they never considered it as a particle before. They never considered light as a particle. They considered it as just a wave, right, that carries photons, energy particles. But they've recently discovered the particle nature of light. So let me talk about that. So they discovered that whenever light of high energy is shone on a metal, electrons get removed from the surface of a metal. So then they said, well, if light can cause an electron to be removed from the surface of a metal, then light has to be a particle as well. It's not just a wave, but it's also a particle. So this is what they call the particle nature of light. So in general, this is what I want you to understand. So one photon will remove one electron. If there are two photons will remove two electrons. This is important because they can actually ask you about the number of photons of light. So you have to know that the number of photons is the same as the number of electrons, because one photon removes one electron, one photon removes one electron, two photon removes two electrons, and so on, right? So if we have got 500 photons will remove 500 electrons, right? But this is provided that the light has enough energy. So if the light has enough energy, a certain number of photons removes a certain number of electrons. Now let's go deeper. Let's talk about that. So let's talk about colors of the rainbow. So we use what we call Rorschach. So we use this to memorize the colors of the rainbow. So there is what you call Rorschach. So there is what you call the red side. So this is the red side of the spectrum, right? And this is the blue side of the spectrum. So this is what we call the spectrum, right? The rainbow colors. So in Doppler effect, it was mentioned that towards the red side, the wavelength is more, right? But towards the blue side, the frequency is more. Remember, frequency is indirectly proportional to wavelength, because we know that the equation, for instance, if you use this equation, the speed of a wave is equals to the frequency of the wave times the wavelength of the wave. If I make the frequency the subject of the formula, notice that it's going to be speed over the wavelength. So frequency and wavelength are indirectly proportional. So meaning that the bigger the wavelength, the smaller the frequency, or the more the frequency, the smaller the wavelength. So towards the blue side, we've got higher frequency, and towards the red side, we've got higher wavelength. Now, I want you to know that whenever we've got high frequency, we've got higher energy, right? I'll explain why. And lower frequency, lower energy. So light towards the red side, whenever the color of the light is towards the red side, the energy is low. But whenever the color of the light is towards the blue side, the energy is higher. So what am I talking about? So there is what you call the energy of the light. So energy is equals to Planck's constant times the frequency. So whenever we've got the frequency of the light and we want to get energy, we use the equation energy is equals to Planck's constant times the frequency. So Planck's constant is found in the formula sheet. So Planck's constant is 6.63 times 10 to the power of 34. So just to correct it a little bit, it's minus 34, right? So it's 6.63 times 10 to the power of minus 34. So this you find in the formula sheet. So you don't really have to memorize this. So notice, the higher the frequency, the higher the energy, because energy is equal to Planck's constant times the frequency. So the lower the frequency, the lower the energy. So what am I trying to say? Yellow, or rather orange light, has got higher energy than red light. Yellow light has got more energy than orange light, right? And also than red light. So violet light has got the highest energy. So this equation tells you the energy of the light. So now what I want you to understand is that different metals have got different work functions. Let's talk about work functions. So work function is represented by WO. So what is work function? Work function is the minimum amount of energy needed to eject electrons from the surface of a metal. So remember, when light of a certain energy is shown on a metal, electrons get emitted, but they will only get emitted if the light meets the minimum energy, right? So if the light is equals to the minimum energy or greater than the minimum energy, that's when electrons will get ejected from the surface of a metal, right? So now, different metals have got different minimum energy that is required. So let's just say, for instance, this metal, let's just say the energy, so it's not realistic, it's just an example. Let's say the work function is 5 times 10 to the power of 2, right? And let's say this other metal, so let me just do something. So let's just say this other metal has got a work function of, so let's just say that's got a work function of 2 times 10 to the power of 2, right? So let's just create fake energy levels for this light. So it's not realistic, right? It's just an example. So let's just say the energy level of this light is 1 times 10 to the power of 2, and let's say this one is 2 times 10 to the power of 2, right? So let's just do that. Let's just say this one is, so okay, let me just remove this stuff. So let's just say this one has an energy of 1, right? For each, it's just going to be times 10 to the power of 2. This is just an example. Let's say this one is 2 times 10 to the power of 2. This one is 3 times 10 to the power of 2. This one is 4. This one is 5. This one is 6. This one is 7 times 10 to the power of 2, right? So now, if I take this red light and I shine it on this metal, will electrons get ejected from the surface of a metal? No, it won't, because it's lower than the minimum energy required, right? Remember, in generally in physics, right, in Newton's laws and even in electricity, work is the energy transferred, right? So wherever they ask for energy, you think of work, or wherever they ask for work, you think of energy, right? So now notice that this is lower than the work function, so it will not eject electrons from this metal. What about on this one? Well, it still won't eject electrons from this metal because it's lower than the work function, right? So now, what about if I take orange light? So the orange light has an energy rather of 2 times 10 to the power of 2. Remember, these are fake, these are not realistic. So this one will have an energy of 2 times 10 to the power of 2. So will it eject electrons from this metal? It won't, because it's lower than the work function. But will it eject electrons from this metal? Yes, it will, because it equals to the energy, the minimum energy that is needed. So what I want you to understand is that whenever it's exactly equals to the minimum energy required, yes, it will eject electrons, right? It will eject electrons, but they will remain on the surface. So these electrons will have no energy. So it will remove electrons from the surface of a metal, but they will just remain around the metal. But if I take something like yellow light, for instance, so the yellow light will have 3 times 10 to the power of 2. So it's bigger than the work function. So if it's bigger than the work function, electrons won't just get ejected. They will have enough energy to move also. So they will have a kinetic energy. So they will not just be ejected, they will be ejected, but they will move away. So they will move with a certain speed. So this is why we have the formula: energy of the light is equals to the work function of the metal plus the kinetic energy, right? The maximum kinetic energy. So let me just explain this. So notice, whenever the energy of the light is exactly equals to the work function, there will not be kinetic energy. So the electrons will get removed, but they will be around the surface of a metal. They will be removed, but they've got no speed, right? But when the energy of the light is bigger than the work function, then it will have enough energy to remove the electrons from the surface of a metal and also to give the electrons a certain kinetic energy. So then electrons won't just be removed from the surface of a metal, they will also have a certain speed at which they can move.
Just before I continue, if you want to be tutored, whether it is online or physically, whether it is the situation where you're struggling in maths or whether it is the situation where you're good in maths but want perfection, take a screenshot or save these details. Whether you're studying Cambridge, which is the UK curriculum, or whether you're studying NSC, which is the South African curriculum, or IEB, or native courses which start from N1 to N6, or any curriculum you're doing no matter which country you're at, we offer tutorials. We've got lessons and practice sessions 5 days a week. We also give you tests once a week so that we can check your improvement.
A certain kinetic energy. So let's talk about something. So remember, the higher the frequency, the higher the energy, right? So now what I want you to be aware of is that every metal has got a work function, meaning that every metal has a minimum energy that is needed to remove electrons from the surface of that metal, right? Every metal also has what you call a threshold frequency, right? So what is the threshold frequency? Remember, we can convert frequency to energy. Whenever we've got a frequency of the light, we can convert it to energy by using this formula, right? So every metal has got a minimum frequency that is required, the same way it has got a minimum energy. So let me just explain this. So now notice that work function, if they don't give us the work function of the metal, they can actually give us the threshold frequency, right? Threshold frequency is the minimum frequency needed to eject electrons from the surface of a metal. It's the same as work function, right? Work function is the minimum energy, but threshold frequency is the minimum frequency that is needed to eject electrons from the surface of a metal. So work function, the formula for work function, notice that work is actually energy, right? So it's supposed to be the same as this formula because this is energy, right? Work function is also energy. So we're going to say work function is equals to H, right? So it's supposed to be the same. But now instead of us having the frequency, we will have the threshold frequency, which is represented as F sub O, right? So the work function is equals to Planck's constant times the threshold frequency for that metal. So every metal has got its own threshold frequency, the minimum frequency that is needed to eject electrons from the surface of a metal. So instead of them giving you the work function of the metal, they can actually give you the threshold frequency. So if they give you the threshold frequency, you can use this formula to get the work function of the metal, right? So light has got different frequencies. Even without us using the energies, we can still tell whether electrons will be ejected or not. So if we're given the frequencies of the light instead, we can compare it with the threshold frequency of the material, right? So if the frequency of the light is smaller than the threshold frequency, electrons will not get ejected from the surface of a metal. But if the frequency is equals to or higher than the threshold frequency, then electrons will get emitted from the surface of a metal. So it's just like work. It's just like us comparing energy and work. But this time we'll be comparing the frequency and the threshold frequency. Let's just do a small example. Alright, so now let's just say these are frequencies, right? Let's say each of these is times 10 to the power of 5, right? So let's say each of these are the frequencies of the light. Let's say the frequency of red light is 1 times 10 to the power of 5. So let's say this certain metal has got a threshold frequency of, let's just say it has got a threshold frequency of 3 times 10 to the power of 5. So if I take a red light and I shine it on this metal, electrons will not get ejected from the surface because this is going to be 1 times 10 to the power of 5. It's going to be lower than the threshold frequency, right? If I take an orange light, still the same, lower than the threshold frequency. If I take the yellow light, it's going to be equals to the threshold frequency. So what will happen? Electrons will get emitted from the surface of a metal, but they will not have kinetic energy, right? They will not have kinetic energy because the energy of the light is equals to the work function, right? Or simply because the frequency of the light is equals to the threshold frequency, right? But now if I take a green light, because the frequency is bigger than the threshold frequency, electrons will not only get emitted, they will also have kinetic energy, because whenever the energy is bigger than the work function, it means the energy is enough to remove electrons from the surface of a metal and also to give it kinetic energy. So that's how it is. So let me go to one more part that will be very important for this topic. Then afterwards, we'll just do some few questions. Alright, let's go back to the previous situation. Let's say all these are instead the work functions, right? And let's say each of these is times 10 to the power of 2. So let's say the work function for this metal is 3 times 10 to the power of 2. So now there is a difference between increasing the energy of the light and increasing the intensity of the light. So let's just say I take a yellow light, right, and I shine it on this metal, right? Because the work function, or rather because the energy of that light is the same as the work function, it will emit electrons from the surface of this metal, right? So now one photon will, one photon will emit 1 electron, right? So one photon will emit 1 electrons, two photons will emit 2 electrons. So let's talk about intensity. If I increase the intensity of this light, what I'm doing is that I'm increasing the number of photons. So let's say I increase this to 10. I've just increased the intensity. So what does this affect? The more the electrons, or rather the more photons I release, the more electrons will get ejected, right? So in other words, if I increase intensity, I'm increasing the number of electrons emitted from the surface of a metal, right? So the higher the intensity, the more electrons will get emitted. That's what you must know. So intensity does not affect the speed of electrons, it just affects the number of electrons emitted, right? So one photon with enough energy will remove 1 electron, right? 2 photons with enough energy will remove 2 electrons, and so on. So if I increase the intensity of the light that has enough energy, it will release more electrons. So if I instead take a red light and I shine it on this metal, because the energy of this red light is lower than the work function, electrons will not get emitted. What about if I increase the intensity? Yes, the number of photons has increased, but all these photons have got less energy than the work function, so electrons will not get emitted from the surface of this metal, right? So I want you to understand that if the light has got less energy than the work function, if I increase the intensity of that light, it will just increase the photons, but all these photons have no energy, so the electrons will not be emitted. But if a light emits electrons from the surface of a metal, right? If a light has got enough energy and I increase the intensity of the light, then more electrons will be emitted from the surface of the metal, right? So increasing intensity increases number of electrons. Now, what does increasing energy affect? Remember, we just talked about it. Increasing the energy of the light affects the speed of electrons. So let's just say this yellow light has got only one photon, right? So let's talk about this the energy. Let's talk about energy. So let's say we take this red light and it has got only one photon. So it will emit one electron from the surface of the metal, right? But because the work function, or rather because the energy is the same as the work function, this electron will not have kinetic energy. But if I take a green light with one photon, it will emit one electron still, right? It will still emit one electron. So increasing the energy does not increase the number of electrons, right? So if I change it from a yellow light to a green light, I'm increasing the energy, but it does not affect the number of electrons. One photon will still emit one electron. So this green light will emit one electron. Now the electron will have speed this time because it's bigger than the work function. If I take a violet light, it is way bigger than the work function. So if I take one photon, it will emit only one electron still, but that electron will have very high speed. So that's what I want you to understand, right? So if I increase the energies, the energy will affect the EK max, because energy of the light is equals to work function plus EK max, right? So if I make this higher, then it's going to be way higher than the work function. So it's going to affect the energy. So I hope you get it, right? So the higher the energy, the more kinetic energy, because the work function obviously remains the same for depending on the type of metal. So increasing the energy of the light increases the kinetic energy of the electron that is emitted. But increasing the intensity does not affect the kinetic energy. Increasing the intensity only affects the number of electrons being ejected. Alright, well, this will be it. Let's go for the questions. Just before you look at the past paper example, if you're interested in knowing the prices of the tutorials, the video that contains the prices and the updated contact details, just in case these ones have changed, is found at the end of this video. Alright, so now let's look at this question. For instance, so they said light is incidented on a cathode, or rather on the cathode of a photoelectric cell connected to a battery and a sensitive emitter as shown below. So you are given this particular diagram, right? So light is shown here in such a way that electrons will be emitted from the surface of that cathode, right? Only if the light has enough energy. So now 10.1, they said what conclusive evidence, let me just do this. So they said what conclusive evidence about the nature of light is provided by the photoelectric effect. So they're just asking you which nature of light is demonstrated by photoelectric effect, right? So if they say what conclusive evidence about the nature of light is provided by the photoelectric effect, it's the particle nature. Alright, this is taken from a past paper. So they said light is incidented on the cathode of a photoelectric cell connected to a battery and a sensitive emitter as shown below. They gave you this particular diagram. So now notice that this is a metal, right? So there's a cathode, so there's a metal. So when light is shown on this metal, if the light has enough energy, electrons will be emitted from the surface of the metal, right? So now let's look at the first question. They said, what conclusive evidence about the nature of light is provided by the photoelectric effect, right? So what conclusive evidence about the nature of light is provided by the photoelectric effect? So here they're just asking you which part of the nature of light. Remember, there is the dual nature of light. There is the wave nature of light and the particle nature of light. So they're asking you which one does photoelectric effect demonstrate, right? So this demonstrates the particle nature of light. So this proves that light is a particle, has a particle nature, right? So whenever they ask you this question, remember photoelectric effect always demonstrates the second one, right? That light has a particle nature. So now they gave you the the work function of the cathode, right? So they gave you the work function of this particular metal. So it's 3.42 times 10 to the power of negative 19. So that is the work function of this metal. So now they say define the term work function. So it's quite easy, right? Work function is the minimum amount of energy that is needed to emit electrons from the surface of a metal. So now they gave you the frequency of the light that is shown, right? So notice here they gave you the work function, but here they didn't give you the energy. They instead gave you the frequency of the light that is shown, right? So if you want to get the energy, you can simply use the formula E is equals to HF, right? So if you substitute F here, you will get the energy. So that is if we need the energy. So, and if the energy is higher than the work function, electrons will be emitted. If it is less than the work function, electrons will not be emitted, right? So that's how it is. So now, if the energy is bigger than the work function, not only will electrons be emitted, they will also have kinetic energy. So now let's look at this question. So now they said calculate the maximum kinetic energy of an electron ejected from the cathode, meaning that this, we can even prove it. So meaning that when we convert this to energy by using the formula E is equals to HF, right? When we use this formula, we will figure out that the energy will be higher than the work function. So it won't be equal, it will be higher, meaning that there will be kinetic energy. So they ask us for the maximum kinetic energy of the electron ejected from the cathode, right? So if they ask for the kinetic energy, then we have to use the formula. So let me just write this down. So before I write it down, we know that E is equals to the work function plus the kinetic energy. So I'm not using a pen, so hence don't mind my handwriting. So this is going to be plus EK max, right? Let me just leave it as EK. So I'm going to write this. So we know that this is going to be the formula. So far we're given the work function, meaning okay, fine. So far we're given the frequency, meaning that we can find the energy of the light, right? We find the energy of the light by saying E is equals to HF, right? So we'll be able to find the energy of the light, and then the work function is what we're given, the work function of the metal. So it will be easy, very easy to find EK. So let me just demonstrate that part. Alright, so here they gave us the work function of the metal, and they gave us the frequency of the light that is shown on the metal. So they want kinetic energy. So we know that the energy of the light that is shown is equals to the work function plus the kinetic energy, right? So EK max. So we have got the frequency of the light, so we can get the energy of the light. We can get it by saying HF, right? And then I'm not going to change this work function into HFO, right? Because we are given the work function. If we're given the threshold frequency, then we would need to change it into work FO so that we can get the work function. We would rather need to change it to HFO, right? So here we're given the work function. So if we're given the threshold frequency, I would have said HFO, but we're not given the threshold frequency, we're given the work function. So this is going to be 3.42 times 10 to the power of minus 19. And then this is going to be plus. So EK max is what we are looking for, right? So let me just write it in symbols for now. So this is going to be work function plus EK max. Alright, so now let's do substitution. So Planck's constant is 6.63 times 10 to the power of negative 34. And then we're going to have times the frequency, right? So we are indeed given the frequency, which is 5.96 times 10 to the power of 14. So now we have the energy of the light. So now this is going to be the work function, which is 3.42 times 10 to the power of negative 19. And then this is going to be plus EK max, which is what we are looking for. So all I have to do is to take this to the other side of the equation. So this is going to end up being EK max is equals to, so this is going to be 6 points. So I'm just calculating it my own way. You can do it your own way, literally no problem. So this is going to be 5.96 times 10 to the power of 14. You are allowed to multiply them, right? as long as you don't round off before the final answer. So my advice in physics is never round off until the final answer. So this is going to be minus 3.42 times 10 to the power of negative 19. So let's get the answer. So EK max will be equals to, so this should be our answer. You can verify that with me. So because it is EK max, kinetic energy is in joules. So what about if they asked for the speed of the electron? So if they ask for the speed of the electron, notice that EK is equals to half mv squared, right? So you can simply get, so far we have got EK, right? So we can easily get the mass. The mass of the electron is in the formula sheet. I believe it's written something like ME, right? In the formula sheet is right there, right? So then you can easily get the speed of the electron. Or if you want, if they ask for the speed of the electron, in this place we could have written it as half mv squared, right? And then what we would have done is just to get the mass of the electron and substitute it here. Then what we'll be solving for will now be v, right? So if when we solve for v, we would have gotten the speed of the electron, right? So remember, whenever the light that is shown has higher energy than the work function, there is going to be kinetic energy on the electron. There is going to be a certain speed. So these are the type of questions that come out. Now let's go to a more deeper question. All right, so now let's go to this question. Now notice notice something. So notice that the M meter, they say the M meter registers a constant current of 0.012 A, right? So 0.012 A. So the ammeter registers a current of 0.012 amps. Now they said calculate the minimum number of photons of light that strikes the cathode in a 10 seconds period. So now notice they are asking for the number of photons. Now we don't have a formula for the number of photons, honestly, we really don't. But remember, the number of photons is equal to the number of electrons that are ejected from the surface of a metal. And we do have the formula for number of electrons. So for us to find out the number of photons, we just need to find out the number of electrons. So every time they ask you for the number of photons, you have to find the number of electrons. Sometimes they can ask you for the number of electrons, sometimes they can instead ask you for the number of photons, which is just the same thing, right? So for us to get the number of electrons is equals to the charge, right? It's equals to the charge divided by the charge of one electron, right? So the charge of one electron, we find it in a formula sheet, but Q, it depends on the scenario. So notice something. They gave us time. So what should we do? They talk about the amps, they talk about time. This usually bothers a lot of students, but it shouldn't. This also comes out in electrochemistry, by the way. They can give you the amps and they can give you current, right, which is amps. They can give you current and they can give you the so they can give you current and they can give you the time. So if this happens also in electrochemistry, all you have to do is to remember the grade 9 formula. Remember, current is equals to charge over time, right? The ones did this. Current is equals to Q over T, right? So I hope you get it. So current is equals to Q over T. So we can easily get Q, and T must always be in seconds. If they give it to you in minutes, convert it to seconds. If they give it to you in hours, convert it into seconds. So they gave you the current and they gave you the time. We can easily find the charge, right? Always remember that. So even if it comes in electrochemistry, if they give you current and they give you time, we can find the charge. Or if you want the current and they give you charge and they give you time, we can easily find the current. Same formula, right? So I hope you get it. Remember, I is equals to Q over T. So forgive my handwriting, I'm not using a pen. So that's how it is. So current is equals to Q over T. So we can get the charge. So the charge is, when we make charge the subject of the formula, Q is going to end up being equals to I times T, right? Q is equals to I times T. So that's what we have. So now we're just going to multiply current and the time. Since it's already in seconds, we don't need to convert it. So if we multiply that, it's going to end up being, the answer will end up being 0.12. You can confirm that, right? So we now have the charge. So now we can easily get the number of electrons. So let me work this out. So let me just go to the whiteboard. So we know that current is equals to Q over T, right? So this was taught in grade 9. So current is equals to Q over T. So far they gave us the current, which was 0.012, and they gave us the time, which was 10 seconds. So if we just cross multiply, we'll be able to find it. So it means that Q will end up being equals to 0.12, right? So that's the charge. Now that we found the charge, we know that the number of electrons is equals to Q over the charge of each electrons, right? So this is in the formula sheet, right? So the number of electrons is equals to 0.12 over the charge of each electron. So in the formula sheet, if you go there, the charge of each electron, I think it's 1.6 times 10 to the power of 19. Yeah, I think 19, negative 19. All right, so let me just confirm that. Let's find out. All right, so now looking at this, we see that we have Planck's constant there, right? Whenever you want to use it. Okay, so okay, what did I do? Okay, so now we're looking for the charge of one electron. Boom, there it is. And remember, when you want to find the mass of the electron, there we go. This is the mass of the electron. So far we wanted the charge of the electron, which is negative 1.6 times 10 to the power of negative 19. So that's what we have, is negative 6 times 10 to the power of negative 19. However, in this formula, we do not put negative, right? So let's find out the number of electrons, which will be equal to the number of photons. So this should be 7.5 times 10 to the power of 17. You can confirm that with me. All right, let's go to the last question. So this is equals to the number of photons, right? So we can even say, therefore, it is going to be 7.5 times 10 to the power of 17 photons, right? So photons. So that's how it is. All right, so now they ask, so this is what they said. They said the intensity of incident light is now increased. How will the change affect the reading on the ammeter? So the intensity is increased, right? So let's talk about this part. All right, so now let's talk about how intensity affects it. So notice that if intensity of the light is increased, it means that I'm actually increasing the number of photons, right? So if I increase the number of photons, the number of electrons that get emitted also gets increased. That's what you must know. So if light is shown on a metal, right, one photon removes one electron. So if I increase the intensity, I'm increasing the number of photons. So it means that more electrons will get emitted, right? So what happens if more electrons get emitted? Notice how will it affect the ammeter. So when we talk about amps, we're talking about current, right? Current is equals to Q over T, right? And then how is Q related to the number of electrons? So the number of electrons is equals to Q over that, right? So I want you to notice something. So if you want, you can even write, so this is another way of writing this formula. Q is actually equals to NE, right? So this is another way of writing the formula. So notice that if I increase the number of electrons, I'm increasing the charge. And if I'm increasing the charge, I'm actually increasing the current. So therefore, the ammeter will read will have a higher reading. Maybe it was 1A, it will become 2 if I double the intensity, for instance. So the ammeter will now increase. So that's how it is, right? So increasing the number of electrons increases the charge, and increasing the charge increases the current in turn, because they're directly proportional. So I hope you get it. Well, this brings us to the end of this video.
Alright, we have reached the end of this video. I have included a playlist of similar type of questions. If you enjoyed this video, please like the video and subscribe to my channel. Any questions you've got or any video you want me to create, please comment below. See you in the next video.